Okay, so let us start the today's session. In the last session, we have started with the vapor power cycle. Okay, so in the vapor power cycle, we have initially seen the Carnot cycle as a vapor power cycle, but it was having some limitations or impracticabilities. That is the reason why, okay, we have studied the Rankine cycle or Rankine cycle we have seen, right? So we have seen the TS diagram, we have seen the schematic diagram for the Rankine cycle. Okay, then we have seen which are the methods to improve the efficiency of Rankine cycle. After that, we have seen ideal reheat Rankine cycle. Okay, so now, okay, we will take the problem based on the Rankine cycle. Okay, so I'll just briefly write down the problem. A steam power plant, a steam power plant, a steam power plant working on Rankine cycle, steam power plant working on Rankine cycle, working on Rankine cycle uses steam at 50 bar, uses the steam at 50 bar. Okay, in the bracket, dry and saturated, dry and saturated, dry and saturated. The steam is condensed, the steam is condensed, the steam is condensed, the steam is condensed at, the steam is condensed at 0.05 bar. The steam is condensed at 0.05 bar in condenser, in condenser, in condenser. Determine its efficiency, determine its efficiency, determine its efficiency. Okay, so they have given the parameters for the Rankine cycle. Okay, then and they're asking to calculate the efficiency of Rankine cycle, right? They're asking to calculate the efficiency of the Rankine cycle. Okay, so let us start. Okay, a steam power plant working on a Rankine cycle. Okay, a steam power plant working on a Rankine cycle uses the steam at 50 bar. Okay, so see, it uses the steam at what? 50 bar. Okay, and that steam is dry and saturated. Okay, that means at the inlet to the turbine, the steam should be dry, right? At the inlet to the turbine, steam should be dry. Okay, so if I brief you, okay, what we have taken in the last lecture. Okay, so if you just clearly see the schematic diagram, okay, for the Rankine cycle, right? So I will just show you that diagram. See, this is basically the Rankine cycle which we have seen in the last lecture. Okay, so this is a schematic diagram. Okay, so whenever there is a problem, it is not expected that, okay, you should draw the schematic diagram. Okay, we are morely focused on the TS diagram, right? So see, in the Rankine cycle, okay, there are only two possibilities, okay, with respect to point 3. If you see the location of point 1, it is same. Location of point 2, it is again same. Okay, location of point 4, it is again same. So there will be the difference in the location of point 3, because point 3, it's the outlet to the boiler or it is inlet to the turbine, right? Point 3 is the outlet to the boiler. You can see this point number 3, that is the outlet of the boiler, and outlet of the boiler is nothing but the inlet to the turbine, right? Okay, so there will be the difference between the location of point 3. See, if you see the point number 3 in this diagram, the point number 3, it is lying on this saturated vapor line. Okay, see, if you just see the right hand part of the curve, it is called as the saturated vapor line. If you see the left hand side of the curve, it is called as saturated liquid line. See, this is a saturated liquid. Okay, left hand side is a saturated liquid, right hand side is a saturated vapor. Okay, so if any point it is lying on the right hand side of the curve, okay, it is said to be dry steam or saturated steam. Okay, it is called as a dry or saturated steam. Okay, so if you see the point number 3, it is lying on the right hand side of the curve. That's why the condition of the steam at point number 3 is said to be dry or saturated. Okay, but when we go to this point number 3 in this particular diagram, if you see the point number 3, it is lying at the right hand side of the curve. Okay, it is basically lying in this region. Okay, it is lying in the right hand side of the curve. Okay, so if such is the case, the condition at the point 3, it is said to be superheated. Okay, so at point 3, what is the condition of the steam? It is a superheated. If you see here at the point number 3, the condition of the steam is a dry steam. If it is lying on the right hand side, it is said to be superheated. Is that okay? Is that okay or not? Let me know. Is it okay? Yes. Have you understood this concept? Is that okay? Have you understood this diagram?
Yes, sir.
Yes, sir.
Okay. Now see, based on the problem, okay, what they're saying, a steam power plant working on a Rankine cycle uses the steam at 50 bar. Okay, and that steam has to be dry and saturated. Okay, the steam should be dry and saturated. Okay, so tell me, I should go for this first diagram or this second diagram? Let me know which diagram I should go, whether it's a first diagram or second diagram. Yes, just now I told you. Which diagram I should refer? I should refer first diagram or second diagram. The steam is dry and saturated. Yes. Yes, let me know which diagram I should refer. I'm waiting for all of you the response. Which diagram I should refer? In the problem, it is dry and saturated. Okay, so in which diagram the steam is dry and saturated? Can you tell me in first or second? I'm waiting for all of you to respond. Yes.
The upper one, sir, the first one.
Yes, it's the first one only because it is clearly written. It's at point number 3, it is dry. And in the problem also, they are asking to have a dry steam. So I need to refer this diagram only. See, I'm telling you, diagram both are same. Only the difference will be in the location of point 3. Point 3, it is lying on the curve. That's why it is dry. Point 3, it is lying on the right hand side of the curve. That's why it's a superheated, right? So let me plot the diagram. Okay, this is point number 1. Okay, here point number 1 is there. So from point number 1, we will move, okay, to point number 2. Okay, the 1 to 2 will move. Okay, after that, we have that heating. Okay, so we'll move like this, right? Now we have reached to point number 3. Okay, so now from point number 3, okay, we'll go down. See, 1 to 2, okay, it's an isentropic compression pump. 2 to 3, during 2 to 3, okay, 2 to 3, what is 2? It's a constant pressure heat addition. 2 to 3, it's a constant pressure heat addition, right? Now, what they're using, a steam power plant working on a Rankine cycle uses the steam at 50 bar. Okay, so at point number 3, we want the steam to be at what? 50 bar. So pressure at point number 3 should be 50 bar. Okay, now you know that pressure at point number 3 is equal to pressure at point number 2, because 2 to 3, it is done at a constant pressure, and that is basically occurs in a boiler. Okay, so I'll just mention here, P2 is equal to, okay, I'll just write down here, P2 is equal to P3 and is equal to 50 bar. Okay, so when you measure the pressure at any point on this line, if you measure the pressure at any point on this line, it is equal to 50 bar. Why? Because we want the pressure at point number 3 to be equal to 50 bar. So pressure at point number 3 and pressure at point number 2, it is same, because 2 to 3, it is done at a constant pressure, and that basically occurs in a boiler, right? So on this line, pressure is 50 bar. Is that okay? Right? Now 3 to 4, okay, we have that expansion. Okay, so we'll expand it. Okay, so this is the expansion which occurs. So this is 3 to 4, right? That expansion. Okay, then we will go to 4 to 1, right? 4 to 1. Okay, that is what? Heat rejection in a condenser. Heat rejection in the condenser. See, 1 to 2, it's isentropic compression. 2 to 3, constant pressure heat addition. 3 to 4, isentropic expansion. 4 to 1, okay, heat rejection in a condenser. Constant pressure heat rejection in a condenser. That means here again, pressure at point number 4 is equal to pressure at point number 1. See, pressure at point number 4 equal to pressure at point number 1. Right? If you see what is given, the steam is condensed at 0 bar. Okay, steam is condensed at 0.05 bar. That means at point number 1, they want pressure to be equal to 0.05 bar. See what is written. The steam is condensed at 0.05 bar in the condenser. That means the pressure in the condenser is 0.05 bar. Okay. So see this upper pressure line, it's a boiler pressure line. Okay, this bottom pressure line, it's a condenser pressure line. See, there are only two pressures. One is a boiler pressure, that is P2 is equal to P3, and second is a condenser pressure, that is P4 is equal to P1, and that is mentioned as 0.05 bar. 0.05 bar. Is that okay? Yes or no?
Okay, sir. Yes.
See, there is no need of any confusion. In Rankine cycle, there are only two pressures. One is a boiler pressure, second is a condenser pressure. Whichever is a higher, it's obviously a boiler pressure. Whichever is a lower, okay, it's a condenser pressure. Now try to understand. Pressure, see, pressure at the outlet of the pump. See, when you see point number 2, okay, see, when you see the point number 2, it's nothing but the outlet to the pump. Point number 2 is nothing but the outlet to the pump, or it is inlet to the boiler. Try to understand. Point number 2 is the outlet to the pump, or it's a boiler. Similarly, point number 3 is outlet to the boiler and inlet to the turbine, right? So, okay, the process 2 to 3 is conducted in a boiler at a constant pressure. That is the reason why pressure at point number 2 is equal to pressure at point number 3. Okay. Similar case is going to happen with 4 and 1. Point number 4, it's the outlet to the turbine or inlet to the condenser. Point number 1, it's the outlet to the condenser or it's an inlet to the pump. Okay. But what happens? Condenser constant, that's why P4 is equal to P1. Is that okay with this one? Let me know. Is that okay? Yes. Is that okay? Yes, all of you, is that okay? Let me know. Is that okay or not?
Yes, sir.
Okay. So now see, let us start. We are supposed to calculate efficiency. Right? We also seen how to calculate the efficiency. Okay, if you just see the formulas we already seen for calculating the efficiency of Rankine cycle. Okay, if you want, I will just show you those formulas. Okay, so you'll be able to just recall those formulas. You can see this we also see how to calculate the efficiency of Rankine. Okay, so I will just write down the same formulas. Okay, so let us start. Let's start. Okay, now let us start. Okay, let us start. Okay, so okay, if you want, we can also start from point number 1, or also we can start from point number 3. Okay, so at any point we can start. Right? Is that okay?
Yes, sir.
Okay, so let us start with point number 1. Okay, let us start with point number 1. Right? See, point number 1, if you see point number 1, okay, it is basically lying on which line? It is lying on saturated liquid line. See, point 1 is a liquid. At point number 1, okay, what is the condition of liquid? Okay, it's the saturated liquid. At point number 1, it is lying on a saturated liquid line. Okay, so if point number 1 is lying on a saturated liquid line, how to calculate enthalpy? How to calculate enthalpy H1? Okay, so enthalpy of a liquid or basically saturated liquid, right, is given by, see, if you just recall the table, okay, which I have plotted. Okay, I will just show you that table which I have plotted. Okay, so okay, see here. So this table we have plotted. I will just show you that table. Okay, so this is a table which we have plotted. Okay, so as to remember the formula. See, now it's a liquid. See, when we see the point number one, it is lying on which line? It is lying on a line where x is equal to 0. See, all of you see here. See, point number one, when you see point number 1, it is lying on a it is lying on a line or lying on a curve where x is equal to 0. See, on this line, x is equal to 0. Similarly, when you see here on this line, x is equal to 1. See, I repeat, on this line, x is equal to 0. Okay, on this part of the curve. Okay, when we see on the right hand part of the curve where x is equal to 1. See, on this line, on this curve. Okay, see, when we see left hand side of the curve, x is 0. When we see the right hand side of the curve, x is 1. Right? Now see, when x is equal to 0, okay, that is basically the liquid. You can recollect. Okay, when x is equal to 0, whenever that is a liquid, how to calculate enthalpy of a liquid? See, enthalpy of a liquid is given by HF. Yes or no? See, I'm telling you very simple. If any point is lying on the left hand side, its enthalpy is HF. Right? Simple. If it is lying on the left hand side, enthalpy is HF. If it is lying on the right hand side, enthalpy is Hg. Enthalpy is Hg. We will come to that point. Now try to understand. As it is lying on this side of the curve, enthalpy is given by HF. Right? Now how to calculate HF? Okay, how to calculate HF? Okay, at point number 1, what is the pressure? 0.05 bar. Okay, so HF, it is nothing but HF. Okay, HF is nothing but HF. Okay, at what pressure? At 0.05 bar. Try to understand. See, we need to calculate enthalpy at point number 1. So enthalpy at point number 1, how will calculate? It is given by HF. Okay, enthalpy at point number 1, how to calculate? Enthalpy at point number 1 is given by HF. That is HF at point number 1, right? And what is point number 1? Point number 1, it is nothing but at point number 1, what is the pressure? 0.05 bar. Is that okay? Let me know. Is that okay? Yes.
Yes, sir.
Okay. Okay. Now, how to get these values, right? How to get this value? So let us see. Let us calculate that value. HF at 0.05 bar. Okay. Now you know that. Okay. At point number 1. Okay. When we see point number 1 or 2 or 3. Okay. See, you check the condition. At point number 1, pressure is 0.05 bar. Okay. So this already I told you. Okay. Table number 1 and 2 we can use when we have a liquid or wet steam or dry steam. See, we can use table number 1 and 2 from the steam table when we have either liquid or wet steam or dry steam, because table number 3, 4, 5 they are only for superheated steam. Okay, so here there is no any equation of superheated steam. Okay, we have either liquid or, see, at point number 1 it's a liquid, at point number 3 it's a dry steam, at point number 4 it's a wet steam. See, on the left hand side it's a liquid. Okay, when we see the left hand side of this curve, okay, left hand side of the or left hand part of this left hand side curve, okay, that is on this side, it is liquid. When we see here, okay, on the right hand side, okay, it's pure vapor. See, here it's a liquid, here it's a vapor. So in between it's a liquid plus vapor, and that is nothing but a wet steam. All right. So when we see on this curve, okay, it's a liquid. Okay, when we see here on this curve, it's pure vapor. See, here it's a pure liquid, here it's a pure vapor. Okay, so in between what? It's a liquid plus vapor, and that is a wet stream, right? Is it okay or not? And if it is on the right on this side, it's obviously a superheated. Is it clear? Is it clear or not?
Yes, sir.
Okay, so see, when we see table number one, sorry, point number one, at point number one, the fluid is liquid. The fluid is liquid. Okay, so as it's a liquid, obviously I need to go for either table number one or table number two. I will go for table number one when I know the temperature. Okay, and I will go for the table number two when I know the pressure. Okay, so see, let us refer that. I just started browsing that scheme. Okay, I already posted this in your group. Okay, you can just refer this steam table by Kurmi. Okay, I just posted a PDF. Right. So see, let us see how to pick those values. Okay, so I know the pressure 0.05 bar. Okay, see, so if I go to table number one, okay, if you see, the first column is based on temperature. You can see table number one, you can use when temperature is known. I don't know the temperature. Okay, so that is the reason why I will go for the table number two. Okay, you can see here, I will go for table number two. So table number two, I've reached, okay, at 0.05 bar, 0.05 bar. Okay, can you see that value? 0.050 value. I'll just annote that. Okay. All of you. Okay. You just refer this. Okay. Can you see this 0.050? 0.050. So this is the pressure. At this pressure, I want HF. I want this HF, right? You can see this value of HF, 137.8. Is that okay? HF, what is that? 137.8 kilojoule per kg. Is it okay? Okay, this is the value of HF. Okay, 137.8. Okay, and what is the unit for that? It's a kilojoule per kg, right? Kilojoule per kg. Is it okay? Yes. Is it okay? Yes, all of you. See, I'm waiting for your response. Okay, so I'll just clear that. Okay, I'll stop it. Okay, so this is the value what I got. Okay, this is the value what I got from the table. Okay, from the table. Okay, so if you want, I'll just write down this as from table number two. Table number two. I got this value from table number two. Why I refer table number two? Okay, but because table number one and two you can use, okay, for either liquid or for wet steam or for dry steam. Okay, and table number one you can use when temperature is known. Table number two when pressure is known. I know the pressure, so I refer table number two, right? Okay, now see during 1 to 2 what happens? During 1 to 2, okay, there is an isentropic compression in a pump. Okay, so during 1 to 2 the fluid get compressed, okay, in the pump. Okay, so how much work, okay, the pump requires? How to calculate that? So in order to calculate that, how to calculate work consumed by the pump, okay, is given by, okay, initial volume, okay, into change in pressure, that is P2 minus P1. Try to understand how to calculate work consumed by the pump is given by, okay, initial volume into change in pressure. Okay, now see, again there will be a question. What is V1? What is V1? Again, what is V1? We require volume. Again, as I said you, as H1 is equal to HF1, H1 is equal to HF1. Similarly, V1 is equal to what? V1 is equal to then VF1. Yes or no? V1 is equal to VF1 then. Okay? Into P2 minus P1 into P2 minus P1. Is that okay? See, if you want, okay, I will just also show you what I had taken in the last lecture. It's a liquid. So how to calculate the volume of a liquid? It is given by VF. Volume of a liquid is given by VF, right? See, understand. Liquid, it is indicated by F always. Liquid is F. Okay. And whenever it's a dry steam, it is G. See, liquid is F and dry steam is G. Okay. So these only you need to remember. So any point on the line where X is equal to 0, we need to take F. Any point on this line where X is equal to 1, we need to take G. Right. So this is only the simple way to understand. Okay. So let us use that. So now V of 1, again, how I should get V of 1? Okay, again, I need to go to the table. Okay, so let us see that. Okay, so I will show you at 0.050, this is the pressure. I want Vf. So can you see this value of Vf? Can you see this value of Vf? All of you, 0.001, 0.001. 0.005. This is the value of Vf. Is it okay? Yes, this is the value I got. Okay, again from which table? This is from table number 2 we got. This is Vf. Okay, and P2 minus P1. Try to understand. P2 minus P1. As I told you always, see this pressure which is given in the problem, it is in bar, right? Bar multiplied by meter cube per kg, right? This bar we are supposed to convert. The bar we are supposed to convert into what? We need to convert that into kilopascal. Okay, we need to convert that into kilopascal. Okay, so simply I will write down 50 is a P2. You can see P2 pressure is 50 minus P1. P1 is 0.05. Okay, but this is in bar, right? This is in bar. And how to convert bar into kilopascal? Okay, just multiply it by 100. Okay, so just multiply it by 100. That is by 10 raised to power 2. Okay, because we want this into what? We want this into a kilopascal. I repeat, see 50 bar. So 50 bar if you want, see in the rough I will do a calculation, right? Let me do that in the rough. Okay, so see here, 50 bar, right? 50 bar, it is nothing but 50 into 10 raised to power 5 Newton per meter square, right? 50 into 10 raised to power 5 Newton per meter square, right? That means, okay, that means how you can write down? So that you can write down as 50, okay, into 10 raised to power 2 into 10 raised to power 3 Newton per meter square, right? 50 into 10 raised to power 2 into 10 raised to power 3 Newton per meter. Okay, so 50 into 10 raised to power 2, you can keep it as it is. Okay, and 10 raised to power 3 Newton per meter square, it is nothing but kilonewton per meter square, right? It is nothing but kilonewton per meter square. 10 raised to power 3 is nothing but kilo, right? And kilonewton per meter square, okay, it is nothing but, okay, kilopascal, right? Because Newton per meter square is a pascal, kilonewton per meter square is kilopascal. Is that okay, all of you? So how to convert bar into kilopascal? Just multiplied by 10 raised to power 2. You can see this. 50 bar means what? 50 into 10 raised to power 2 kilopascal. So what? That is only what I take. Okay. Yes. Is that okay or not? Is it okay or not? Yes. Is that okay? See, if you want, I will just write down here one more step, not a problem. So E is equal to Vf. What is Vf1? It is Vf at 0.05 bar. Vf at 0.05 bar. See, what is Vf1? Vf, and what is the pressure at point number 1? See, what is the pressure at point number 1? It is 0.05 bar into P2 minus P1 into P2 minus P1, right? But thing is, I written one more step, okay? But these two has to be in kilopascal. This has to be in kilopascal, right? So that I put. Okay, so what answer we got? Can you tell me what answer we received for this one? Okay, so WP we have received as 5.01 kilojoule per kg. 5.01 kilojoule per kg. See, it's a 5.01 kilojoule per kg. Okay, so this much work is being consumed by the pump so as to compress a liquid from 1 to 2. We need to compress it from 1 to 2. So this much work is consumed, right? So see how to calculate WP again. Okay, WP, if we want to calculate, we can calculate this as H2 minus H1. See, this formula I already told you. You can see this has been already explained. WP is H2 minus H1. You can see. Okay, so WP we know 5.01. 5.01 is known, right? See, this is 5.01 is equal to H2. I supposed to calculate minus H1 is 137.8. Okay, so from this I will get the value of H2. From this I will get the value of H2. So I got the value of H2 as 142.81 kilojoule per. Okay, so 142.81 kilojoule per. See, WP, how to calculate the work consumed by the pump? It is difference between the enthalpy at the outlet minus enthalpy at the inlet. So is it okay, all of you?